Okay, so let's see question number 3 from paper 1. It is given that a conducting square loop initially lies in the xz plane with its lower edge hinged along x-axis. Only in the region y greater than equal to 0, that means this region, the right side of the xz plane, is having some time dependent magnetic field pointing along z direction. It is also indicated z direction. The magnetic field as a function of time is given as b naught into cos omega t k cap, where b naught is constant. The magnetic field is 0 everywhere else. At time t equal to 0, the loop starts rotating with constant angular speed omega about x-axis in the clockwise direction as viewed from the plus x-axis. That means the loop is rotating in this direction, ignoring the self-inductance of the loop or whatever it is. Which of the following plots correctly represents the induced EMF in the loop as a function of time? So see, to find out the induced EMF, we have to first find out net magnetic flux crossing through the loop. So first we'll assume any general position of the loop. Let's say the loop is starting at time equal to 0, the loop is starting to rotate from the xz plane. At time t, the angle it will make with the xz plane, that is omega t. So this is any random position of the loop or random angular position of the loop. So magnetic field is along z axis. So the area of this square loop, if I consider to be A, then what is this projected area? So through this projected area only of the square loop, the magnetic field is crossing perpendicularly. So this area multiplied with the magnetic field, that will be our magnetic flux. If the area of the square loop is A and it has made omega t angle, the projected area along xy plane or the plane which is perpendicular to the z axis, that is, this area is going to be our A sine of omega t. A of sine theta, so theta is omega t, so A sine omega t is this projected area. So magnetic flux, I can write magnetic field multiplied with the projected area, that is A sine omega t. So B is also given as a function of time. It is given that V naught cos omega t into A sine omega t. So this phi B I can rearrange. V naught A by 2, I can multiply 2 in the numerator and I will get 2 cos omega t into sine omega t, that is sine of 2 omega t, that is our magnetic flux. Now induced EMF or epsilon, that is rate of change of magnetic flux, but there is a negative sign in front of it. So phi B if I put, so then it is d dt minus of d dt of V naught A by 2 sine 2 omega t. So V naught A constant will come out of the differentiation, and ultimately I have to differentiate sine 2 omega t, that is 2 cos 2 omega t multiplied with omega. So what I'm getting, minus B naught A omega cos 2 omega t, that is the induced EMF. Now we have got our induced EMF as a function of time, that is minus of B naught A omega cos of 2 omega t. So we'll just plot it. See, when time t equal to 0, that time the value of induced EMF is cos 0, but there is minus sign, so it is minimum. So maybe it will start somewhere from here. It will be 0. The induced EMF value will be 0 when the value of time will be pi by 4 omega, because the value of cos 2 omega t that time will be cos of pi by 2, so it will be 0. Value of time when it is pi by 2 omega, that time the induced EMF is cos of pi, but there is minus sign, so it is maximum. When the value of time is 3 pi by 4 omega, that time also the induced EMF will be 0, because that time it will be cos of 3 pi by 2, that is 0. And when the time is pi by omega, that time again the induced EMF will be minimum, because that time it will be cos of 2 pi, but there is minus sign, so it is minimum. So the cycle will run like this. The entire cycle will be like this. And if I put the time snap here, this is pi by 4 omega, this is pi by 2 omega time, this time is 3 pi by 4 omega, and this time when it is again becoming minimum, that time is pi by omega. So ideally the graph should be like this. It will continue like this, right? But the thing is, see, for one revolution of the loop, when the loop is starting from here, it is coming here, then again this is the half rotation of the loop, this is another half rotation of the loop. So for the first half rotation, it is crossing through the magnetic field. So magnetic field is present, it is not equal to 0. So there must be some induced EMF in this region when it is crossing. When the loop is rotating in this region, that time some induced EMF will be produced. But to the left of it, the other half of its motion or rotation, that time it is not crossing through any magnetic field, because that in this region magnetic field itself is 0. So the induced EMF will also be 0. So how much time it is taking to cross through the magnetic field region? This entire angular displacement is pi. So the time it is taking, it is pi by omega. Other pi by omega to 2 pi by omega, that time there is no induced EMF. So in this graph, whatever we have plotted, we have to erase this part. That means we have to erase from pi by omega to 2 pi by omega part. Again it will come to the magnetic field region. That time there will be existing induced EMF. Again it will be stopping after half of the revolution, and then it will continue like this. So there will be gap. So here there is no induced EMF. Again here there will be no induced EMF. So it is matching with our option A. So option A is the correct answer. Now let's see question number 4 from paper 1. Now this question is actually not that tough question. It is very simple question, a straightforward question. So if you have studied the Vernier scale properly, you'll be able to answer this question. Okay, let's see. Figure 1 shows the configuration of the main scale and the Vernier scale before the measurement. So this is before the measurement, it is indicated. So there is no zero error. It's clearly visible. Zero error is not there. Is zero. Zero error is actually zero. And the second configuration is shown after measuring some diameter d of a tube. The measured value you have to find out. But the thing is, Vernier scale, whatever least count we have normally studied, in this instrument the least count is different, because we have to count. See, in the main, this is the main scale. The upper one is the main scale. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The total 10 divisions the main scale. That is of course okay. So each small division is 1 mm for the main scale. But the catch is, for the Vernier scale, let's see, there are how many divisions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The total 10 Vernier scale division. The total 10 Vernier scale division is matching with how many main scale division? 1, 2, 3, 4, 5, 6, 7. 7. So 10 Vernier scale division, VSD I am writing, that is matching with 7 main scale division. So what is the value of one vernier scale division? One vernier scale division, that is 7 by 10 of main scale division, and we know that main scale one small division is equal to 1 mm. So we can write 7 into 1 by 10 mm is the one vernier scale division value, that is of course 0.7 mm. One vernier scale division. Now the least count for this instrument is one main scale division minus the value of one vernier scale small division. So one main scale division is 1 mm minus one vernier scale division we have calculated, that is 0.7 mm. We'll just put that. So 1 minus 0.7 mm, that is 0.3 mm, is the least count of this measuring device or this vernier scale. Now we'll just see the configuration number 2 where some measurement is taken. We'll find out what is the main scale reading. Main scale reading is, it has just crossed the division number 1, so main scale reading is 1. What is the vernier scale reading? Vernier scale reading is which division of the vernier scale is exactly aligning with the main scale, that is this one, exactly aligning with the main scale. So our vernier scale reading is also 1. So what is the total measurement? Total measurement, main scale reading plus least count into vernier scale reading, that is 1.3 mm. 1.3 mm is 0.13 centimeter. So our answer is option number C.